Hey guys, welcome. Yeah, so in this video, I'm going to give you an example of the third and final Euler substitution. And as I said in the previous two examples, the most important example to watch is example 0, because there we look at all three Euler substitutions big picture, and we come up with three useful equations for x in terms of t, and we're going to need one of them here. Yeah, okay, cool. So what we said in example 0 is for the third Euler substitution, when we encounter square root of ax squared plus bx plus c, where a and b are not equal to 0 and c is greater than 0, c being greater than 0 is what triggers the third Euler substitution, then we said when c is greater than 0, we let this guy equal x times t plus root c. So that means that in this example, which by the way is the same integral as example 1, and so you can do this integral using the first Euler substitution, or as we'll see here, the third Euler substitution. But yeah, with what we wrote on the right side, what we should claim is that this here is equal to xt plus 1, and that's because c, which is 1, is greater than 0, and clearly root 1 is 1. Yeah, okay, cool. Now, as I said, in example 0, we came up with three useful equations for each Euler substitution of what x should be. And so for the third Euler substitution, starting from this here, we figured out that x had to be equal to b minus 2t root c divided by t squared minus a. Tootsie roll? No. Okay, yeah, that means in this specific case, since a, b, and c are all 1, we should let x should be equal to 1 minus 2t over t squared minus 1. And of course, with this x, we see that dx will have to equal quotient rule on this, right? So that's minus 2 times right? Fairly straightforward. Okay, and so dx will have to equal, what is it going to be? Minus 2t squared, and then plus 2, and then minus 2t plus 4t squared. Now notice minus 2t squared and 4t squared combine to a positive 2t squared, so I could do this. And of course I haven't written the denominator of this guy or dt yet, but these guys have a common factor of 2. So if I could factor out a 2, then I could write minus t plus 1 like that. So what we had is the same as this, and of course in the denominator t squared minus 1 squared, and then dt. Yeah, okay, cool. So we found a replacement for dx that's all in terms of t. That's nice. But our denominator here is not all in terms of t, because in xt plus 1, there's an x right there. So we need to figure out what to do about that. That's a fairly easy fix, right? Because if x is right there, right, then xt, right, xt will have to equal, actually I'll do it right here, why write so much? So xt will be a t there and a square there, right? Okay, and then xt plus 1 will be, well, add 1 to the left side, so add 1 to the right side. But a plus 1 here is the same as writing plus t squared minus 1 and then extending this denominator, right? Okay, sorry. That plus sign I should hike up like that. Yeah? Okay, but then that means xt plus 1 is equal to, we have a minus 2t squared and a t squared, so that's minus t squared. And then we have plus t, right? And then minus 1 divided by t squared minus 1. But I want to factor out a negative 1 from this. So when I do, I could put a parenthesis here, turn this into a minus, turn this into a plus, close the parenthesis there, right? And I won't forget that we have t squared minus 1 in the denominator, so there we are. Okay, cool. So then we are now ready to rewrite our integral all in terms of t. First, 1 divided by xt plus 1, which is 1 divided by the square root quantity, will be 1 divided by xt plus 1, which is 1 divided by this, which is the same as the reciprocal of this. So I'll take the negative and write it in front of the integral. This minus sign is that minus sign, and then otherwise I'll write the reciprocal of that, which is t squared minus 1 over t squared minus t plus 1, right, like that. And then I need to multiply this by dx, where dx is this guy here, right? Well, dx leads with a 2, so I'll write the 2 in front of the integral with the minus sign. But the rest of dx is going to be right? Cool, cool, cool. Now look here. Some nice things happen. Boom, 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 bam. So there we are, and we need this space, so that means now our integral is this guy, which is, he is negative 2 times integral of simply 1 over t squared minus 1 dt. Okay, so that's just a little bit of partial frac, right? So partial fraction decomposition would lead us to write the following, which is 1 over t squared minus 1 is equal to alpha over t minus 1 plus beta over t plus 1, right? And getting common denominators on the left side amounts to requiring that alpha times t plus 1 plus beta times t minus 1 be equal to 1, right? Okay, and if we let t equal 1, then we get 2 alpha is equal to 1, from which we conclude alpha is equal to a half. And if we let t equal negative 1 in this equation, we get negative 2 beta is equal to 1, from which we get beta is equal to negative a half. So alpha here is a positive a half, and beta is a negative a half. Got it. Okay, so that means that the integral here could be written as positive 2. I'll tell you what we're going to do about the minus sign in front of the 2. But positive 2, and then 1/2 over t plus 1 minus 1/2 over t minus 1 dt. So I had this minus sign distributed to these guys, which means we'll have to swap, right? The negative of a minus b is b minus a, and that's what I've used to rewrite these guys like that, having swallowed that minus sign, yeah? And of course I could factor out a 1/2, and if I do, I could write a 1 here, right, and a 1 here, and this 2 will go away. All right. So then our answer is going to be the natural log of, using the log quotient rule, the natural log of t plus 1 divided by t minus 1 plus c. Only one little issue, which is our integral had x in it. It didn't have t in it, so we need to get back to x. How do we do that? Well, we had from this here that to start, this had to be true, which is we had to write that root x squared plus x plus 1 had to equal xt plus 1. Okay, if this has to be true, then xt is equal to negative 1 plus the square root quantity, and then t has to be that, right? Okay, cool. But we don't just have t here, we have t plus 1. So t plus 1 is going to be, so this is equal to t, right? So t plus 1 is going to be add 1 here, but adding 1 right here is the same as writing x over x. So I could just write plus x and extend this. So t plus 1 is going to be x minus 1 plus the square root of x squared. This is equal to t plus 1. Okay, now t minus 1 is a little bit more work. So t t was minus 1 plus root x squared plus x plus 1. So t minus 1 is going to be minus 1 over here, but this had a denominator of x, so just as before, it's minus x over x. So I could write like this. This is t minus 1, right? But there's something that we could do here in the numerator, which is we could factor out a negative 1. If we factor out a negative 1, what that'll mean is I could write x plus 1 here, and then a minus sign here, and a negative in front of all of that. Now, although, because it's understood that the log argument has to be positive, I casually use parentheses. We need absolute values around the logs, right? In fact, in my log videos, I explain why it's important to have absolute values around logs. In any case, I'm telling you this to say, when we put absolute values around the argument, this minus sign here is going to go away when we put absolute values. First of all, t plus 1 divided by t minus 1 is going to be this here divided by this here. When we divide them, the x here and the x there are going to go away. And so it's just going to be this numerator divided by this numerator. So I could put the minus sign in front of this quotient, this minus sign, but when I put absolute values, I could get rid of it. So what I'm saying is our final answer is the natural log of t plus 1 is x minus 1 plus root x squared plus x plus 1 divided by x, but again, I will not divide by x because when we divide by t minus 1, the x's will cancel. So I'll divide instead by x plus 1 minus root x squared plus x plus 1, and then plus c. Now look here. If you look at this answer, it's not the same as the answer we found in example 1. Because in example 1, we had the same integral, but we used the first Euler substitution. Even though the answer here is not identical to the answer there, if you multiply by conjugates here, then you'll be able to transform this answer to look exactly like the answer in example 1. So they're different forms of the same answer, is what I'm saying. Yeah? Cool. All right. Otherwise, as I said, this is the final video on Euler substitutions, and I hope you've enjoyed them and you've learned a lot, and keep watching. Take care.